hangata. So I will do it the long way, then we try to come up with the shorter version, which is the argument one. So suppose we have y equals to 2x, 2 to the exponent of x, and we want to reflect this in the line y equals to x, which means that we have xy and we are going to have exchange of yx. Now, what does this mean? This means that what we have in the domain, and here on this side we have the range, what was in the domain on the first image will be the range of the second image and vice versa. So on this side we are going to have range, and on this side we are going to have domain. Just keep that in mind. I know it's maybe a bit challenging to understand it for now, but it's very important to take note of this. So a function has its unique behaviors. When we sketch this, we sketch it in a way that just a rough sketch, it's going to look like this. And this part plays a role in a way that we have a 1 here, a positive 1. And we have the asymptote, which is the x-axis. Is the asymptote. So if we rotate this about this line, what are we going to get? According to this, we say x values will become y values and y values will become x values. So the domain will become the range and the range will become the domain. This is what we are saying. So if the x values are going to become the y values, if we have a positive 1 here, this is the line y equals to x. It's our mirror line because we are reflecting about that line. Then this is the y value, y equals to 1. So which means that for an image, we are going to have x equals to 1. They exchange behaviors. That's the first argument we can have. And we know that we have an asymptote, which is the line x-axis, or the line we call it y equals to 0. So which means that x equals to 0 will be our new asymptote for the image. And our curve should move towards the asymptote. We can even have a point maybe somewhere here, and as you can see, it's probably, if we put a 2 here, then the corresponding value will be a 4. So we have a 4, then we have a 2 somewhere here. Then this will exchange behaviors. What are we going to have? We are going to have values that are like this. This 2 will go in the y-axis, and this 4 will go in the x-axis, and they create a point. So when you join, you will move towards the asymptote, and that's how we sketch. Okay, you are arguing mathematically, and you are arguing very careful. Okay, now I understand how re deal ka di behaviors, not just in this function, in all the functions. Once we reflect about this line, the behavior di change kaofela. Okay, the behavior di change kaofela. Now re batla bona gore how can we turn this into a function that will suit this one, right? Which is the inverse. And that's what we want now. We want the inverse. And the inverse this function has reflected about the line y equals to x. So more le x, more le y as ratio, more le x, le y, more le y, le x. It's a vice versa. So le mona, instead of writing y, re x. Instead of writing x, re y. So ke yona equation e re nang le yona no tshwanetseng re solve. Re na le this operator re bitsang gore ke a log operator ko maths. So this one re berekisa fela when we want to drop exponents. So we use it when we want to drop exponents. Ane? So yang so ke tla boela mo equationing ena ne. In fact a re tshware re tlise ka mo re tla bereka ka yona when it's on this side. Re bereka so ha re na le say 5 to the exponent of x and then re kenya log got this whole thing. Exponent e tlo dropa, then re tlo salela fela ke 5 ke yona ntho e tlo etsahalang ka mogare ga log. So a re apply mo calculating re bona gore vele ke net. Ha re na le 5 is say to the exponent of 2 ke 25. Then re tlo reng a re na le log of 5 to the exponent of 2 ke 1.39. a re capture number ene 1.39. So hankantsha this exponent ka itlisa ka mo re tshwanetse re tholeng is our answer 1.39 ne. So ke ntho e 1 la bona. So this log is responsible for go dropa eng, for go dropa an exponent. Okay, so go etsa equation ya rona e nne easy gore re solve, re tshwanetse re applying log. When re apply ka mo the right hand side, everything re etsang is affected on both sides. What you do on your left, you do it on your right and vice versa. So the next stage mona ke gore re tlo reng log of x. Purpose ya go introduce a log ke gore re batla dropa eng, this y. Mara re batla dropela kae ka montle ga log so that re ka kgona go e solve. Then re na le log e multiplying le y, then go easy go solve equation. Re tlo divide both sides ka the log of 2. Then re salela again ke log of x divided by log of 2. Then re ngwala ka a nicer way, re reng log of re na le e ko tlase re ngwala mo tlase sona, then re na le x mo godimo re ngwala mo godimo so. Then re na le log of x base 2 ke ka mokgwa re bitsang ka teng log x base 2. Okay, you must recall something. When I started this, I told you we want to avoid these steps, right? We want to avoid these steps, so we have to find a way to avoid them. So here's a way. If you are given an equation like this, y equals to 2x, and you are asked to solve this whenever we have this transformation, as long as you know the name that okay, the reflection would be what, you just have to write log of x base 2. This is the base and this is x, so x will be at the top and the base will be at the bottom. Then you are done, right? Because this will just be like 2 marks, unlike you know, having to go through all of these steps. So this is a nicer way of getting your answer. Okay, so firstly what you're going to show is that you have the original equation, you do the transformation. After you are done with the transformation, then you just say y is equals to log of x base 2. Done. Now